The lecture number 5 of physics 401A. So last week we derived, or rather we discussed, the method of calculus of variation, and this week we will derive the basic equation of Lagrangian formulation of classical mechanics, which is called the Euler-Lagrange equation, using that method of variation. So using that method of variation, when someone wants to derive this Euler-Lagrange equation, basically we have to go through, or rather we have to use a basic principle, which is known as the principle of Hamilton, okay, or the principle of least action. Okay. Although, I mean, as you can understand from our past discussion, that it should be simply stationary. That means it should be either maximum or minimum, locally extremum conditions. Okay, but it is, I mean, traditionally it is known as the principle of least action. Okay. Now the statement is that every mechanical system is characterized by a function L of the generalized coordinates q1, q2 up to qs. So you easily can understand that S is the number of degrees of freedom of the system, and the generalized velocities q1 dot, q2 dot up to qs dot and t. Okay. In a schematic way, we are just writing for brevity L as a function of q dot t. Okay, without just writing every single index. And the mechanical system, for the mechanical system, L is defined, and the motion or mechanical evolution of that system will be governed by the following rule, which is that between two given time instants, initial and final time instants, t1 and t2, and two given sets of generalized coordinates, q1 and q2, the system always chooses the path of least action to evolve. Okay. Now here I am saying just that two given sets of generalized coordinates. It can be a number of sets of generalized coordinates. Okay, that is just, I mean, somehow traditionally it is said that between the two it will always choose the least one. So basically, if we give you a set of collection of choice, okay, let's say 5 or 6 paths, it will always choose the path of least action. So basically, if we give you all possible such sets of generalized coordinates, the system will choose the path of least action, okay, for its physical evolution, where action is defined as S, which is integrated over L dt. Okay, so here I say it chooses the path of least action, and action is mathematically is nothing but the integral of L dt. Now you can easily make the correspondence between S and J of our discussion of last week. Okay, L as f, t as x, and q as y, q dot as y dot. Correct? Okay. Now L is defined as the Lagrangian of the system. Okay. Now let me ask you one small question over here. Here we in general say for all physical systems, Lagrangian contains only q and q dot. So Lagrangian is something we don't know exactly what it is till now, but one thing we know, that it is something very important for determining the exact evolution of a mechanical system, and then we say it is a function of q dot and t. Now can just with all these knowledges you have gathered till now, can you somehow say that why Lagrangian should contain only q and q dot and not q double dot, q triple dot, etc.? Of course there should be t, but for q and its derivative, I am just asking why we have to just stop until q dot and not q double dot, q triple dot and higher order derivatives of q. Okay, so just think about that. Okay. So now you have understood, I hope, the principle of least action. Now using that principle, we will derive the equation of Euler and Lagrange. For simplicity, we assume that our system has only 1 degree of freedom. degree of freedom. Once again, you know now what is the meaning of degree of freedom, or rather 1 degree of freedom. That will just be specifying having one couple of q dot. Okay. Now the objective, our principal objective for this whole formulation is to determine q as a function of t using the extremum condition that we all know. Only that we can predict the position of the particle at any time t, and we can and if you know q, then you also know q dot. If you know q as a function of t, you also know q dot as a function of t. Then basically the total state of the system can be specified, right? Now let's do, or rather let's follow the method of variation. Okay, let us suppose another path of evolution which is slightly displaced from the real path. So the real path here is the deep blue one, and the another path which is neighbor but very differing from the real one slightly. So as you know that the slightly means from our previous discussion, this will be another one where the curve, this curve can be written not only as a function of t but as a function of t and a smallness parameter which we called alpha, right? Here I am not going into that detail. Now assuming that you know what is exactly going on over there, I directly use the symbol del. Okay, so for that we can write the generalized coordinate for that neighboring path will be q prime t is equal to qt, which is the generalized coordinate of the real path of evolution, plus delta qt. Okay, so delta q, if you just remember, this is nothing but alpha times eta of t, this type of thing, right? Okay, and we also know that this is called the variation. So in this type of variation, we always have this intrinsic variable which is time over here to be frozen, right? So for a given time we are just changing the smallness parameter alpha, and we will really reach to different type of neighboring curves. So here I am just taking any of those curves which is not the real one but the neighboring one. Okay. However, we all know that we have to follow these initial and final constraints, that the virtual or the virtual displacement or the variation of q at initial time instant and the final time instant should vanish, because the unreal path or the artificial path should also meet the real path at initial and final point. This is by our construction, right? Now, principle of least action simply says that if the evolution path is slightly varied, of course this means that virtually varied, with respect to the real one, then delta s is equal to 0. So then you can say that it is varied with t as frozen over here. Okay, and then you can say your q will be q plus delta q, q dot will be q dot plus delta q dot. So this will be the new action. So this will be your new Lagrangian, lq plus delta q, comma q dot plus delta q dot and t, and integral over this over time integration will be given the corresponding action. And this is the action for the real path. Okay, and we are claiming that this will be equal to 0, because this is the virtual variation, or this is the variation or virtual variation or virtual displacement of the action. Okay, since we know now delta operator and time, they are independent of each other. Basically delta operator means you are changing the smallness parameter alpha, and time means you are changing directly the time. Okay, so and they are mutually independent. Okay, so that's why they commute. And finally you can write, so if you just write every L of q plus delta q as like del, so you can write this whole thing as LQ q dot t plus del L del q delta q plus del L del q dot delta q dot, right, minus L q q dot t, and then this L q q dot t will be will be vanishing because there is a one plus and one minus, and then the term which is resting over here is simply this del L del q delta q plus del L del q dot delta q dot times dt integration over this time, I mean integration from t1 to t2, that will be 0, right? So that is the condition for stationary action. Again we know delta q dot is equal to delta of dq dt, and ddt and delta q, they are also commuting with each other. That is simply because ddt is the total time derivative or total change with time, but on a given or specific trajectory. Whether the trajectory is real or whether the trajectory is artificial, that is not the thing, but once one trajectory is chosen, ddt is defined for that. On the other hand, delta gives you the navigation from one trajectory to the other. That's why they are also commuting. Okay. Then you can simply say del q dot is equal to ddt of del q. Okay. Now, if you now substitute this thing in this second term, just a minute, in this term, for example, and you say delta q dot is ddt of delta q, then finally you can do an integration by parts of the whole thing, where the first term will simply be del L del q dot delta q evaluated at t1 and t2, okay, minus integration from t1 to t2 ddt of del L del q dot delta q dt, right? Now this one will vanish because delta q has a 0 value at both t2 and t1, so this is 0, so you simply have this one. Okay, so now if you just come to this equation number 1, then substituting this value of this, I mean expression of this second term using this equation number 2, you have finally this integration over t1 to t2 del L del q minus ddt of del L del q dot times delta q dt is equal to 0. So that is the condition for stationary action. Okay. Now the above integral vanishes for any value of delta q, because delta q's choice can be arbitrary. We haven't said any specific value of delta q. We said any arbitrary. We have started with any arbitrary neighboring path, and dt is also non-zero in general and can have arbitrary values, right? But for every choice of delta q or dt, this integral should vanish. That is the condition of stationary action. So then the only one possibility is that this integrand should vanish identically, and then you have the condition of stationary action can be reduced as a condition on L, which was a condition of stationarity for this integral of L dt. Now you has a reduced condition on the function L itself. This is simply ddt of del L del q dot minus del L del q is equal to 0, and that's exactly your Eular-Lagrange equation, which is the governing equation of Euler-Lagrange, or rather Lagrangian formulation of classical mechanics. Okay. Now if the system has more than 1 degree of freedom, we can derive identical equation for every qy. So I already asked this question in the context of the lecture, I mean the method of variation, and some of you tried. Okay, so basically the answer is, I am trying to give you here, if you have, let's say, more than one type of generalized coordinate, so you have more than 1 degree of freedom, so you have s number of couples, q and q dots, so qy, q1 q1 dot, q2 q2 dot, like q is up to qs dot. Then you can write in this equation number 3, you can write a sum, or you can write a sum of the terms. Let's say del L del Qy minus d dt del L del Qy dot times delta Qy dt plus del L del Q, dt. So this term will be there will be a sum over I for that. That means if you are just trying to expand the whole thing by saying Q1 Q2, that will be then integration over T1 to T2 del L del Q1 minus del ddt del L del Q1 dot times delta Q1 dt plus del L del Q2 minus ddt del L del Q2 dot times delta Q2 dt plus up to this, up to Q, so I is equal to S. So there will be S terms like that. Now the thing is that you can always say, as the Qy's are independent of each other, you can change the trajectory from the real one to an artificial one by a specific choice, for which you just change any one, only one of the Qy's, only one single. Let's say I change Q1 only. All the other Qy's will be unchanged, right? Then all the other delta Qy's will be 0. Only the delta Q1 will be non-zero. So for that, what will happen, that we can say that this integrand should vanish. You can again say that for another type of specific choice can be made. If you, let's say you just change your Q2 to Q2 to delta Q2, and you keep all the other Qy's unchanged. If you do this type of trick, then basically for every single Qy you can prove this type of equation, right? And as you know that all of them are independent, then basically, in order that this thing to be generally true for arbitrary choices of delta Q, okay, rather there will be delta Qy's, you can always say that all of them, all of the integrands will separately be vanishing. Otherwise it is not possible. If any of that is not vanishing, then what will happen, if we make the specific choice that we just change that Qy, and we keep all the other Qy's unchanged, then this condition would be difficult to manage, right? Because then it will not be 0 for that Qy. Let's say this is not 0, then this will not also be 0, because we have changed for that Qy. So basically this will then not be identically satisfied. Then this will have a very special condition that under that integration this will be 0. So that functional arbitrariness will not be available or will not be attained there. So that's why for every I, for multidimensional multidimensional problem or problem with multi degrees of freedom, for each degrees of freedom this should be true. Okay. The last comment on that is, we said previously our goal is to find Q as a function of t, for which this is minimum, but we derive one condition for L only. So are we done? The answer is yes, we are done given now. So this is just, we have now reduced the extremity condition or the extremum condition or the stationarity condition in terms of L. Now in order to find Q as a function of t, what we have to do? We have to solve this. So for that we have to know what is the really functional form of L in terms of Qy and Qy dots and also t, and then only you can solve this equation to find Q of t. Okay, so this is not the final step of solving the problem. This is just the equation, or this is just a reduced or an equivalent condition of the stationarity, the condition for stationary action. Okay. for the final trajectory, you have to solve this. So, for this lecture, I end here. So, in the next lecture, I will try to find a form of Lagrangian for a mechanical system. Okay, thank you very much.